Imagine you're training an artificial intelligence to solve the hardest, most complex math problems in the world.
Right.
And for months, it's getting smarter, making these huge leaps in logic. And then suddenly, it just stops. It completely hits a wall.
Just plateaus entirely.
Exactly.
Yeah.
But not because it ran out of data and, not because you ran out of computing power. It's because the AI is literally using the wrong kind of ruler to measure its own brain.
Yeah. Which is a wild concept to wrap your head around.
It really is. So welcome to you, the learner. Today is August 6th, 2026, and we are embarking on a deep dive that, well, it completely flips how we understand machine reasoning.
It is a genuinely profound shift in the landscape, I think. We're looking at a state-of-the-art paper from a team of researchers at Tsinghua University in ByteDance,
Right.
and it's titled Beyond Euclidean Clipping, Overcoming Exploration Collapse in LLM-RL via Riemannian Isometric Policy Optimization.
Okay, that is a mouthful.
I know it sounds like a massive wall of dense academic jargon, but we're going to break it down because this isn't just some minor iterative tweak to some existing code.
Right.
This is a foundational rethink of exactly how AI measures its own learning process.
Okay, let's unpack this, because to understand how this team fixed the AI, we first have to understand the rut that the entire industry has basically been stuck in.
Yeah.
If you've been following how large language models are getting so good at long horizon tasks, things like multi-step math or complex coding, you already know that reinforcement learning is the engine driving it.
Right. RL is the core.
Exactly. But right now, the standard engine everyone uses is something called PPO-Clip, which stands for Proximal Policy Optimization. And according to this paper, PPO-Clip is causing a massive failure called exploration collapse.
Yeah.
So what exactly is failing under the hood here?
Well, to really grasp exploration collapse, we have to visualize the sheer vastness of what we call the state action space. When an AI is given a highly complex multi-step math problem, it doesn't just, pull the answer from memory. It has to navigate this massive branching tree of decisions.
Like a maze, basically.
Exactly. At every single step, there are countless possible paths it could take to get to the next step. And some of those paths are obvious and safe, but others are rare, unconventional, and entirely necessary to actually reach the final correct answer.
Right, like finding a clever shortcut in geometry that you wouldn't normally think of right away.
Precisely. Now, PPO-Clip's main job is to keep the AI's learning process stable. Because if an AI changes its behavior too wildly from one step to the next, the whole training process can just collapse.
It just forgets everything.
Right, catastrophic forgetting.
Yeah.
So PPO-Clip restricts how much the AI can change its policy, its strategy for choosing actions at any given moment. But here is the fatal flaw.
Yeah.
By strictly limiting those updates, it accidentally forces the AI to rapidly concentrate on a very narrow set of safe, high-probability actions.
So it's basically taking the path of least resistance.
Yeah, exactly.
It finds something that sort of works,
Yeah.
and then just stubbornly refuses to try anything else. It makes me think of a stand-up comedian trying out new material.
Ooh, I like that.
Right. Imagine a comedian goes on stage, tells one mediocre joke that gets a very mild chuckle. And instead of taking a risk and testing out a totally new joke that might actually get a standing ovation, they just repeat that same mild joke endlessly for an hour.
Right.
Sure, it's a safe bet to get a chuckle, but they are completely stuck in this mediocre loop because they're terrified of bombing.
That analogy actually captures the mechanics of the failure perfectly. In RL, the algorithm finds a high-probability exploitation token, your comedian's safe joke, and it just keeps reinforcing it.
Just milks it.
Exactly. It aggressively suppresses the model's ability to search the rest of the space. So those rare but vital actions, the potential standing ovations, they're left entirely unexplored. And in these increasingly challenging long-horizon tasks, sustained exploration isn't just, a luxury or a bonus feature. It is an absolute necessity. If you don't explore, you collapse. You hit a ceiling where the AI simply cannot solve harder problems.
I know the industry has recognized this plateau, right?
Uh-huh.
And they've tried to fix it. The paper mentions previous baselines like DAPO, where researchers basically just tried to raise the clipping boundaries.
Yeah, DAPO is a good example of that.
In my comedian analogy, I guess that's just giving the comedian more time on stage and hoping they eventually try something new.
That's a really fair way to put it. DAPO and similar frameworks, they tried to encourage exploration by artificially widening the boundaries of what the AI was allowed to update.
Okay.
But as the researchers of this new paper point out, those fixes were entirely heuristic.
Just guesswork, basically.
Yeah, they were band-aids treating a symptom.
Yeah.
They didn't offer any real theoretical understanding of why the AI was too scared to explore in the first place. And that's because they were still operating within the fundamentally flawed mathematical framework of PPO-Clip.
So if tweaking the boundaries was just a band-aid, let's look at the actual disease.
Let's do it.
The paper points out that if we dive into the underlying math of PPO-Clip, there's a massive geometric mismatch. And this seems to be the core discovery, right?
Absolutely.
The researchers argue that PPO-Clip implicitly measures how much the AI's policy is changing by using a flat Euclidean metric.
Yes, and this is where we have to look closely at the math. PPO-Clip relies on what's called an importance ratio.
Okay.
It simply takes the probability of a new proposed action and divides it by the probability of the old action. If it sets a clipping boundary at a ratio deviation of, say, 0.2, it treats every single 0.2 deviation exactly the same. It assumes that an equal ratio deviation means the policy changed by an equal amount everywhere in the AI's brain.
Wait, let me make sure I'm actually following this. If it's a flat ruler, it means the algorithm thinks it's moving, say, 1 mile in its learning space. But because of the underlying probability landscape, the actual distance it moved could be wildly different.
Exactly.
It feels like trying to use a flat, two-dimensional paper map to measure flight distances over a 3D globe.
Oh, that's a perfect way to visualize it.
Because on a flat map, the distance between two longitude lines at the equator looks exactly the same as the distance between those same two lines way up near the North Pole.
Yes.
But in physical three-dimensional reality, those distances are totally distorted. Are you saying PPO-Clip is basically navigating a 3D globe with a flat map?
What's fascinating here is how that map analogy reveals the exact mathematical blind spot of the current models.
Really?
Yeah, the flat 2D map is the Euclidean geometry that PPO-Clip assumes. It assumes the space of all possible policies. What we call the statistical manifold is flat and uniform.
But it's not.
No, it's not. The true discrepancy between probability distributions isn't flat at all. It is governed by a concept in information theory called Kullback-Leibler, or KL, divergence.
Okay, KL divergence. I've actually seen that pop up in a lot of these papers. What does that actually mean for the AI's map?
At its simplest, KL divergence measures how much information is lost when you use one probability distribution to approximate another.
Okay.
And the key thing to know is that KL divergence induces a curved, non-uniform geometry known as Riemannian geometry.
A curved geometry.
Right. In this curved Riemannian space, the actual geometric distance of an update depends heavily on how likely the action was in the first place.
So the landscape itself is warped based on probability?
Precisely. If you are in a high probability region, meaning the AI is looking at an action, it already strongly favors the distances expand.
Expanding distances. Okay.
Yeah, a tiny change in probability actually represents a massive leap in the geometric space. Conversely, in low probability regions, those rare unexplored actions, the distances shrink.
Oh, wow.
So when PPO-Clip stubbornly applies its flat Euclidean ruler to this curved Riemannian globe, it causes highly pathological destructive training behaviors.
The researchers actually break down the numbers on this, and honestly, seeing the math laid out is what finally made this click for me.
The numbers are stark, yeah.
They show just how absurd the distortion gets. Let's walk through their example, because I think it helps.
Sure.
They use a standard clipping boundary of 0.2. Now imagine a high probability action, something the AI already likes. Maybe it has a starting probability of 0.8.
Right.
Under PPO-Clip, because of the flat math, that 0.8 probability is allowed to be updated all the way to 0.96. That is an absolute increase of 0.16 in a single training step.
Which is an aggressively large update.
Yeah.
In the context of the curved space, that update consumes a massive amount of what we call the trust region budget.
Rust region budget.
Yes. The trust region is essentially the safe allowance the AI has to change its mind without breaking its past learning.
Right. So the common action eats up a huge chunk of the budget.
Exactly.
But then look at a rare action. An exploration token that might actually hold the genius shortcut to the math problem. But currently, the AI only gives it a probability of 0.01.
It barely notices it.
Right. And under that exact same flat Euclidean PPO-Clip rule, that rare action is tightly, severely restricted. Its update is capped at a maximum of just 0.012.
Yeah.
That's an increase of only 0.002.
And that exposes the core injustice of the algorithm.
Injustice is a good word for it.
Under the true curved Riemannian geometry, those rare actions are systematically receiving virtually zero trust region budget.
They get nothing.
They are starved. They are legally not allowed to grow, even when they are highly informative and valuable. Meanwhile, the already common actions are allowed to grow aggressively.
It's insane.
It is a mathematical starvation of new ideas. This guarantees premature policy concentration, which is exactly why the exploration collapses.
Here's where it gets really interesting, though, because this team didn't just write a paper complaining that the Euclidean ruler is broken.
No, they didn't.
They built a new ruler. They propose a completely new way to accurately measure and guide the AI's learning space, called RIPO, Riemannian Isometric Policy Optimization.
Yes, pronounced RIPO.
Oh, RIPO.
The authors intentionally chose that to highlight how policy improvements should propagate smoothly and evenly across the curved manifold, rather than in these jagged, distorted jumps.
A ripple in the curved space. I really like that.
It's very poetic for a math paper.
It really is. And the engine driving RIPO is a mechanism they call RIC, Riemannian Isometric Clip. So how does RIC actually fix this starvation problem?
RIC entirely discards the flat Euclidean assumption.
Tosses it out.
Exactly. Instead of using a fixed static ratio boundary, it dynamically adjusts the clipping boundary based on the local probability simplex.
Okay, probability simplex.
Let me break that down. The probability simplex is just the landscape of all possible choices the AI has at that exact moment.
Okay, got it.
RIC looks at that landscape and calculates the exact true geometric distance on the curved Riemannian manifold.
So it's measuring the real distance.
Yes. It ensures that every single update, whether it's for a heavily favored common action or an underdog rare action, consumes the exact same budget of the trust region.
It essentially functions like a progressive tax system or maybe a balanced grant program for the AI's ideas.
That's a great way to think about it.
Right, because under the old PPO-Clip system, the rich got richer. The dominant established ideas took all the funding, grew by 0.16, and just monopolized the system.
Yeah.
But RIC steps in and says, no, the dominant ideas are going to get their growth mathematically constrained so they don't take over, while the rare underdog ideas are going to get a much larger budget to explore and prove their worth.
Exactly.
Every idea gets the exact same geometric grant to state its case.
That captures the dynamic perfectly. And we can look at those exact same numbers again to see RIC in action.
Let's do it.
Under RIPO, for that high probability action of 0.8, the dynamic clip constrains the maximum updated probability to 0.92.
Okay, so 0.92 instead of 0.96.
Right. That is noticeably tighter and less aggressive than PPO-Clip's 0.96. It deliberately reins in the dominant action.
And what happens to the rare action? The one stuck at 0.01.
Under RIPO, that rare action is allowed to leap to 0.024.
Oh, wow. 0.024.
Yes. That is double the growth that was allowed by PPO-Clip. And most importantly, both of those updates, the common one moving to 0.92 and the rare one moving to 0.024, they consumed the exact same geometric distance.
They cost the same.
Exactly. They used the same trust region budget. The ruler is finally measuring true distance.
That is just such an elegant way to force the AI to keep its mind open.
It really is.
But you mentioned earlier that there's another layer to this. Beyond just forcing exploration, this isometric clipping creates a massive statistical benefit for how the AI learns, right?
It does, yeah, and this gets into the stability of the model. In off-policy reinforcement learning, there is constantly a tug-of-war, a critical trade-off between bias and variance.
Okay, bias and variance.
Right. PPO-Clip creates a situation with wildly uncontrollable variance because of the chaotic way it handles that long tail of rare actions.
Ah, okay.
And when variance is out of control, the AI's learning updates become chaotic, which can cause it to unlearn good behaviors, that catastrophic forgetting we mentioned.
Right.
But the researchers prove mathematically that geometric isometry, meaning equal geometric distances for updates, implies statistical homoscedasticity.
Okay, stop right there. Homoscedasticity.
I know, it's a big one.
That is a phenomenal word for Scrabble, but what does it actually mean in plain English for the AI?
It essentially means that the variance becomes uniform and predictable regardless of where you are in the probability landscape.
Uniform variance.
Yeah. By guaranteeing these isometric updates, RIC equalizes the contribution of every single sample the AI looks at.
Yep.
Because the variance is uniform and controlled, the AI's learning path becomes highly stable.
That makes total sense.
And because it's actively exploring more rare samples, the bias is substantially reduced. So it strikes a mathematically perfect balance between exploration, finding novel, new answers, and exploitation relying on known, good logic.
So the theoretical math on the whiteboard is stunning. It solves the geometry, it solves the variance.
Yes.
But a beautiful theory doesn't always survive contact with actual silicon.
Very true.
We need to look at the data to see if RIPO actually makes AI demonstrably smarter in the real world. And the testing setup the researchers used to prove this was incredibly rigorous.
It was very comprehensive. They didn't just, test this on one small niche model to get favorable results.
Right.
They evaluated RIPO across 4 different large language models of varying scales and architectures, specifically including models like Qwen 3 and Llama 3.2.
Heavy hitters.
Exactly. And they put them through the gauntlet of 7 different competition-level mathematical reasoning benchmarks.
And we are talking about benchmarks like AM, the American Invitational Mathematics Examination, which is notoriously brutal for AI because it requires intense, multi-step deductive reasoning.
Exactly. And the gains they recorded were massive. If you look at their primary results table, RIPO achieved up to a 60% relative improvement over GRPO on the AME24 benchmark for the Qwen 1.7b base model.
Wow, 60%. Let's quickly define GRPO for the listener because that's an important baseline here.
Certainly, GRPO stands for Group Relative Policy Optimization.
Okay.
It's a very popular alternative to PPO, where the model generates a group of different possible answers and scores them relative to one another to figure out which reasoning path is best.
So it compares them.
Right. It's heavily used in state-of-the-art reasoning models. But even against GRPO and against all the other algorithms that tried to use heuristic clipping tweaks, RIPO consistently achieved the best average performance across the board.
That's incredible. I was looking at the training dynamics section, figure 1 of the paper, and the efficiency of this is almost hard to believe.
It's striking, isn't it?
Yeah. They show that RIPO trained for just 40 steps completely surpasses the performance of the baseline GRPO trained for 200 steps.
It is functionally 5 times more token efficient. That means it requires vastly less compute and time to reach a higher level of reasoning.
And the gradient norms, which, for the listener, is basically a measurement of how violently the model's internal weights are swinging around during training, they show that RIPO is almost entirely fluctuation-free.
Yes, the stability is visible.
The older algorithms have these pronounced oscillations, these huge spikes, where the AI is basically getting mathematically confused. But RIPO is just this smooth, steady climb. It proves that stabilizing the geometry truly stabilizes the AI's brain.
If we connect this to the bigger picture, though, the most compelling piece of evidence isn't just the speed, it's the depth of the reasoning.
Yes, I was just about to bring this up because the PASIC-K analysis absolutely blew my mind.
It's fascinating.
I think this is the single most important piece of data in the entire paper. Let's explain PASIC-K first. Essentially, you give the model K number of attempts to solve a complex problem, and you see if it manages to get it right at least once out of those attempts.
Correct. It is a stress test to find the intrinsic capacity limits of the model.
Right.
It shows you how broad the model's reasoning space actually is before it just starts repeating itself.
Right. So the researchers took the base Qwen 3.8b model and tested it on the AME25 benchmark.
A very tough benchmark.
And the data shows that under the old algorithms, the model completely plateaus after 16 attempts. Pass at 16.
Yeah.
Even if you give it 32 attempts or 64 attempts or even 128 attempts, the success rate just flatlines.
It just hits a wall.
It hits a solid brick wall. Its intrinsic reasoning capacity was completely tapped out because, like our comedian, it just kept exploring the exact same 16 narrow collapse pathways over and over again.
But then they apply RIPO.
With RIPO, the model continuously scales up. It never plateaus at 16.
It just keeps going.
It finds new paths at 32 attempts. It finds more at 64 attempts, all the way up to 128 attempts, ultimately hitting a 60% success rate on AME25.
Incredible.
RIPO literally shatters the AI's previous reasoning boundaries. The PASIC-K analysis visually proves that the AI isn't just getting faster or more efficient at guessing, it is actually getting deeper and wider in its ability to navigate complex logic. It is structurally smarter.
And we have to recognize that the researchers explicitly set out to prove this isn't just some neat trick that only works on math
Right, it's
competitions.
not a one-trick pony.
Exactly. They wanted to prove this was a fundamental correction. So they took RIPO and tested it on long horizon coding tasks using rigorous benchmarks like code forces and Taco,
Mm.
which require the AI to write complex functional software.
Okay.
And then they tested it on multi-hop search tasks using benchmarks like Preview QA and Hotpot QA, where the AI has to synthesize information across multiple disparate
And the
documents.
geometry fixed those too.
It did. RIPO consistently outperformed the baselines with significant verifiable gains across all of these different domains.
Wow.
What this definitively proves is that the geometric mismatch they identified the error of applying a flat Euclidean metric to a curved Riemannian space is a universal law of AI learning.
It's not a math quirk.
Exactly.
Yeah.
By fixing that underlying geometry, you universally elevate the model's ability to reason, regardless of what subject matter it is trying to learn.
So what does this all mean for you, the learner, listening to this deep dive right now?
Yeah, why does it matter?
It means that the foundational architecture of how artificial intelligence explored ideas is shifting under our feet. The
Absolutely.
next time you sit down and prompt an AI to solve a highly complex, multi-step problem, whether you're asking it to architect a piece of software, or balance a complex financial model, or synthesize a massive amount of medical research, this underlying shift to Riemannian geometry means the AI won't just regurgitate the first safe answer it stumbles across.
It won't just tell the safe joke.
Exactly. It will actually have the architectural capacity, the geometric budget to deeply explore the problem space. It will be mathematically empowered to follow the rare, vital threads of logic and find a truly novel, robust solution for you.
It fundamentally elevates the AI from being a simple, frightened pattern matcher trapped in a rut to an entity that is capable of sustained, balanced, and courageous exploration. What stands out to you about this shift in how we mathematically define learning?
For me, it just leaves me with this one lingering thought. If simply changing the underlying geometric assumption of how an AI measures its own learning, just swapping out a flat ruler for a curved one, can unlock this much unprecedented, boundary-breaking reasoning power.
Yeah.
What other fundamental everyday mathematical assumptions in AI architecture are just flat Euclidean approximations waiting for their mind-bending Riemannian revolution?
Now that is a truly fascinating question to ponder. It reminds us that in artificial intelligence, just like in life, the map is not the territory.
Beautifully said. Keep exploring the curves, and we will catch you on the next deep dive.